Well, Michael, I'm glad to see you have this nice little graph, and we're going to actually look at the slope of the line at 0.84.
0.84.
Right there.
Exactly. And so this is our inverse sine function, and we know it looks like a sideways sine wave, right? And I put in a few more numbers here just to make it clear. So the sine function, you know, if we take 1/2 cycle, it goes from minus pi over 2 to plus pi over 2, takes the maximum value of 1, so the inverse function is only defined up to x equals 1.
Yeah, because at 1, the slope of the sine is 0, and we take the reciprocal, it goes
to infinity.
right to infinity.
And you see that in the picture. It looks like, oh, the slope is very steep there.
Yeah.
So let's check out the formula. It turns out we can do this easily from the chain rule.
Yeah.
Which is nice. And I like to say the word easy, because if you set it up right, it actually is easy. So let's give this sine inverse function, give it a name. Let's just call it g of x. Okay. So what do we know about g of x? Well, how does g of x connected to sine?
Well, it undoes what the sine does.
Yeah, so if I take the sine of g of x, sine and g of x, they just cancel each other, and I get x.
In fact, in high school, we used to do that. You'd have a bunch of numbers, and you'd look up the signs, and sometimes you have questions where they gave you the sine values, and you'd have to look up the numbers. So in fact, it's exactly going back to x.
Those were the good old days when we looked up things in a table. Now people would program. I'm going to mention this because if you're programming and you try to find sine to the -1 in your library, it won't be there. It'll be either called arc sine or a sine, short for arc sine.
And that leads back to how do you do it for more complicated functions.
Exactly.
So let's go.
Well, you remember how to differentiate. What's the derivative of sine?
Cosine.
Cosine. Chain rule says I leave the g of x in here, and I multiply by what?
The derivative of g of x.
Which is g prime.
And g prime refers to g dg by dx.
Exactly.
Which is what we want.
Now, what's the derivative of x?
Uno.
1. So look at that. Here's g. Here's g prime. If I move this over there, I've got a formula for g prime. This is equal to 1 over cosine of g of x. And if you like, this is 100% correct, but 100% not very useful. This is the cosine of sine inverse of x. So here's my sine inverse function, way, way back there. This is the formula for g prime.
Ah, now I got to jump in here. This looks horribly messy.
It is.
But what does it mean? It means if you give me the value of the sine x, I'm going to look up what x you got for that value of the sine, and that's like an angle. So now I got to just take cosine of an angle.
Right.
But I know what the cosine of an angle is.
So you can look up that number.
So I can look up that number. And we also know what sine inverse is. So we're in good shape because we can connect the sine with x directly.
Now, Matt, if you notice, if this cosine was a sine instead, the sine and sine inverse would cancel.
Correct.
Or if this was a cos inverse, then the cos and cos inverse would cancel.
Yes.
So wouldn't it be great if I could rewrite a cosine in terms of a sine? Do you
Well,
remember any formulas for that?
Cosine squared plus sine squared equals 1.
Cos squared plus sine squared.
Put in an x or something, because otherwise
Okay.
it looks funny.
Oh, you know what? I'm going to put a little g there.
Oh, gee, okay.
Or if you want, how about y? With my bad handwriting, it looks the same.
Yeah, why?
So now cosine of y is going to be a square root of 1 minus the sine of y. I'm going to write it this way, sine of y, all squared.
Yeah, and we know what the sine of y is from here.
Exactly.
It's equal to x.
So let's put down this formula. This is the square root, 1 minus sine of sine inverse of x. I'm going to write it out in painful notation, all squared.
Aha, so this is obvious what this is. Backwards and forwards, forwards, backwards, it just gives you the initial independent variable.
So this is 1 over square root 1 minus x squared. So this thing is this simple little algebraic formula, 1 over the square root, 1 minus x squared.
And this, and when we apply the chain rule, and we did that before, it's nice, we did it all fine, but this kind of funny business here, because it's mixing, if you like, the functional mappings between the inverse and some other thing that's related to the initial function.
Right.
And so that looks kind of funny in many textbooks. But this is the thing that you always do, and it depends on the fact that when you get this cosine, you can use this relationship between sine and cosine.
Exactly.
That's not always the case, to make it so simple.
Sometimes we're lucky and it works out to something simple. Other times you only get some really messy formula that you just have to compute.
You just have to compute, but we know how to do that.
Yes.
Because we can get out our toothpicks.
Exactly.
And we know how to compute the slope. So this is a big toothpick, but you get all these little toothpicks. And you got a picture of the function.
So if I take g prime of 0.84, I know this is equal to the 1 over the square root of 1 minus 0.84 squared. I don't know what that is, but I'm pretty sure it's going to come out to 1 over 0.54, which is about 2.
Let's see. 0.8 is
0.64.
0.6. 0.6 squared is 0.4. I don't know.
Square root of 0.4 is about
Point.
See, we'll let someone else do the math.
You can't do it real easy. You know what? It's really complicated to do this in your head quickly, but square roots especially.
Yeah.
All right, that's another discussion for another time, but I think we've really got it. Remember your toothpicks.
I'm going to show you just something fun because it's a quick, easy one. If I had redone this with a hyperbolic sine, it has an inverse. This becomes plus.
Plus.
And
Right.
that's the only change. Isn't that amazing?
Yeah. That's related to what we did geometrically between the circle and trig functions
Exactly.
and the hyperbola for the hyperbolic
Exactly.
function.
Because this equation for the hyperbolic function is almost the same, except for a sign change here.
That's right. Good stuff.
Good stuff.